Welcome back. In this lecture, we will define a search problem. And so here are our objectives. All right, so, to talk about some of the basics with search is sometimes we're not given an algorithm to actually solve the problem, but rather we get a specification and we need to search for a solution. And typically you could think of this as you have what is often referred to in AI as an agent, and that agent is in a current state and it has to carry out a series of actions to get to some goal state, some desired end thing. And an example of this you could think of in just some simple route planning. You go to software like Google Maps, you enter in your current location, or the GPS just figures it out, and you say, hey, I want to get to Tempe campus, and I want to get there with these restrictions. Maybe I only want to take a bus, or maybe I want to walk or take a Uber. And what the software does is it's searching through the space to try to figure out the best way to get you to that goal state, which is you being at the Tempe campus. And so what often happens is a mathematical structure known as a graph is a way to represent the problem, and we can represent the individual states as nodes in that graph. And that's what we'll talk about today. And of course, there could be multiple ways to do this. All right, so going back to the notion of having criteria for an agent and its environment, we can look at how the standard search problems we're going to describe today meets that criteria. So here we're going to just basically be a flat environment where the states are explicitly defined. So we're not really pushing for a notion of uncertainty here. And we're assuming this is fully deterministic and it's observable, and there's just clear goals that the agent needs to obtain. And that we basically are also assuming things like perfect rationality, and that we're having all the knowledge. And to keep things simple, in these scenarios, we're considering a single agent. So someone, again, the canonical example is just entering directions in a system to figure out where to go. And this could be a human with Google Maps, a robot navigating a room, and so on. Those are really common things. Okay, so what does a state space problem consist of? So first we have a set of states, and some of them are going to be called start states, which is where you begin. You have a set of actions, and the actions is what the agent takes to move from one state to another. And the action function takes in the action in the current state, and it gives you a new state. So if my agent is going to turn right, the agent is going to transition into a function where the agent is oriented to the right. A set of goal states, so these are the states that you want the agent to reach to have solved the problem. And then a criteria that specifies the quality of an acceptable solution. So, for example, if we're talking about route planning, maybe you have criteria about how much gasoline you use or how many stops you want to take along the way. All right, so here we have a simple example. We have a robot that is at space A and is trying to get to goal G. And so we have here A, and we could say that this whole representation of this of a state right now is everything you see here, and we've noted the robot is at location A with that red rectangle. So then we have a different state, which is the goal state, which is location G. So this is the goal state, again represented as what you see here in the picture. And along the way, there's going to be other states of the robot being in different places. And so maybe we say that, if you're given in state A and you're looking to move left or right, so if he moves left, it's going to be in a state where the robot is at C. If the robot takes the action to move right, it'll be in the action, or it'll be in the state where the robot is in at location D. All right, so now that we have an idea about what states look like, we're going to define how we create the graph based on these. So let's talk a little bit of simple graph theory. So graph, you have a set of nodes and you have a set of arcs or edges. And you say that two nodes are a neighbor, so node 2 is a neighbor of node N1 if there is an arc from N1 to N2. So pretty simple. And a path is just a sequence of these nodes such that there is an arc between every pair. And given the start nodes and the goal nodes, a solution is a path from a start node to a goal node. And so then we can define this notion of cost associated with the arcs, and that would be part of the input. So if you think of the driving example, the cost is perhaps how much gasoline it takes you to get from point A to point B. And we can look at the overall cost of a path as the sum of the costs of the individual arcs. And an optimal solution is a solution, a path from the start to the goal node where that cost is the lowest possible. There's no other path between the start and the goal node that has a lower cost. Then it's optimal. Okay, so let's get back to a state. And basically, in the state, you need to include enough information to determine, actually what is the next state, whether the goal is achieved, and the cost to have gotten there. And so there's, several options for this. You want it as simple as possible, but if you lose information, that is an oversimplification. And what happens there is if you have two states that are indistinguishable, they are actually the same because the state is defined based on the attributes that you include in there. And so if I don't differentiate between one building that costs a lot more to get to than another, the system will think they're equivalent and it will give an improper answer. Okay, so getting back to this example problem. So again, the robot is at A and it wants to get to G. And we can look at the series of relationships among the states where the state is defined as, in that picture, what location is the robot in? And so we could see that robot at location A, which is initial here, its neighbors, and I'll do circles, are B, C, and D. So let's go back and look at the diagram. So there's A, and it can go through, this looks like a door here, it can go to B, it can go to C, and it can go to D. And so simply repeating this process for all the nodes gets us this graph, this state space graph. And the numbers on the arcs in the graph, we can go back and look. This is corresponding with the distance between two of the nodes. So you see from going from A to D, you've got 1, 2, 3, 4. And here, yes, sure enough, there is a 4 right there. Okay, so very straightforward creation of a graph. We have weighted the arcs based on the amount of time it gets, or amount of distance it takes to get from one node to the other. And now we have this kind of compact representation. The other thing, let's say that we have restrictions on the robot's movement and we only let it go certain directions down certain hallways in the scenario. So we don't want to let it go back for whatever reason. Maybe we have a bunch of robots and we don't want them to crash into each other or something. You could use what's called an acyclic graph. The robot can go from A to D, but it can't go back the other way. And so if you think again of something like Google Maps, how are states defined? So we have a single start and goal location, and let's say the cost is estimated time. And so the state needs to include a notion of direction because the cost depends on directions, such as, if you turn left and stuff. So let's give another example. So we say that Rob is on a grid, and Rob can move up, down, left, or right, and needs to collect coins without running out of fuel, and you want him to end up at location 1-1. So here is, where Rob is at now, and then for 1-1, somewhere in the lower left-hand corner of the grid, Rob wants to move there. So you have states. What do you want to put in your state? Well, you want to have the positions. So you want to have the X and Y of where Rob is at. Now, that is not enough information to define a state because it's going to be very different if Rob is at a certain location with a lot of fuel or a little bit of fuel. So let's say that Rob gets, just a couple spaces away from the goal state, but he's out of fuel. Well, Rob can't move anymore at that time, and so there is no transition out of that state, even though the agent is very close to the goal. So we have to account for the fuel. Now, what else do we want to collect? Well, there's a bunch of coins, and so we have coins C, 1, 2, 3, and 4, and you could just represent those in this problem as a Boolean value. We'll say it's 1 if Rob has picked up the coin, and it's 0 otherwise. So at the beginning of the game, Rob could be at a location, he doesn't have any coins, and these are all zeros. And as Rob proceeds through this grid and picks up coins, Rob could revisit a space later in the game, and he could be in that same location, but in a different state, because maybe earlier when he was there, Rob didn't have coin C1, and later on he does. And so the goal is going to be at location 1-1 and with some amount of fuel and, has collected the coins. And so we could look, and here in this diagram, the coins are labeled as either being true or false. So initially, let's look at this very first state. So in these state diagrams, you often see this kind of lone arrow that's coming from nowhere. If you see something like that, that means it's specifying an initial state in these type of diagrams. So notice Rob is at location 5-8, and here is 5-8. So the next thing is the initial fuel, which I guess is just assumed to be 6. So Rob has fuel of 6. And we're saying in the initial state, Rob actually, we're going to say he already has C2. So here C2 is a true and the other ones are false. Now, if Rob moves up, the agent moves to this location, 5-9, right here. Okay? And so here you see he winds up at 5-9. And to move one space, let's say in this game you expend one thing of fuel, notice Rob's fuel dropped to 5. There were no more coins picked up, and so there is no change to those last 4 values. And it proceeds from there. And as you see in this diagram, it builds out as all the different scenarios of what Rob can do on moving up, down, left, or right. All right, so let's do one more example before wrapping up this lecture. Let's say we have a robot cleaner. 2 rooms, 1 cleaning robot. Rooms can be either clean or dirty. And the robot can make the room that it is in clean. It can move to the other room. So it has a sucking action and a moving action. And the goal is to have both rooms be clean. So how many states are there and what are they? Well, let's kind of draw this out. So we can say that a state consists of, let's just say room number. So the first value is room, which room the robot is in. And then we want to say if the room 1 is clean, so that'll be true or false. And then we'll have room 2 is clean. And that's going to be true or false. And then I'll put in a different color here. This is true or false. true or false, and then I'll just say 1 or 2. All right? Great. So with that in mind, let's say what's the initial state? Well, the rooms really aren't distinguishable, so we'll just say the robot starts in room 1, and both of the rooms are not clean. Okay, so there's your initial state, and we have this arrow coming out of nowhere. All right, so there's 2 actions the robot can take. It can do the sucking action, or it can do move. If it does the sucking action, well, the robot still is in room 1, but room 1 is now clean, so that's true. However, room 2, nothing happened, so that's dirty, so that's false. Okay, so there's that state there. Now, if the robot moves, it's a different state. It's going to be in room 2, but both rooms are still dirty. All right, so now the robot is in room 1 still, and it just cleaned it. So there's 2 actions from there. The robot can either suck, and if the robot does another cleaning action, well, nothing happens. The room's already clean. So we can have this arrow to itself. Notice I did not have to add another state. Now let's say the robot moves, and if the robot moves, it's now in room 2, but room 1 is clean. So notice up here, this is a different state because room 1 was still dirty. Going below here, room 1 is clean, but now room 2 is still dirty. So that's what happens when the robot moves to room 2 after cleaning room 1. Okay, well, let's go to the other side. Let's go to what happens considering the other scenario where the robot is in room 2 and everything is still dirty. Well, if the robot decides to clean room 2, it's going to go to a state like this. So if it does a suck, it's going to stay in room 2. Room 1 is still dirty, but room 2 is now clean. All right. So if it moves, if it goes from 2 back to 1, well, everything's still dirty, so now it's going back to the initial state. All right, so now let's go down to the last level. So let's see, the robot is in room 2, and room 1 is clean and room 2 is dirty. Well, if it moves back to room 1, that's kind of going back where it came from, right? Because it just switched rooms. Now, if the robot decides to clean, if it does a sucking action, it's going to still be in room 2. Both of the rooms are clean. Okay, and that is the goal state. So sometimes we'll put something like a, little star by it. All right, one last one to figure out. If the robot is in room 2 and room 2 is clean, it can either move or it can clean. So if it's in room 2 and room 2 is clean and it cleans again, that's the same thing. It's going to do an S. Now if it moves, it's going to be in a state where it's now in, running out of space here, room 1, with room 1 being dirty and room 2 being clean. This is the only state, or this is one of 2 states that is missing. Okay, so if it's in room 1 and then it moves back to room 2, it will just go back. But if it decides to suck, it's going to have another goal state. And that is going to be, should have made these so big. Then it's going to be 1 TT. And that's another goal state. Okay. Now, of course, if it's in the goal state, you could say it could take further action, but there's really no point in modeling that because since we define that as a goal state, the problem is done once it reaches there. All right, so that's all we have for this lecture, introducing you to how to define a search problem. Thank you very much.